Hi, welcome to another lecture on business mathematics. Today we are going to continue our conversation about exponential and logarithmic functions. This is going to be part 3, and we are going to talk about logarithms. So let me remind you what we have done so far. I have summarized everything in this table. So when you are multiplying some number so many times, you use the exponential notation. That is what b to the power of n mean, where b is the exponent, b is the base, and n is the exponent. And then we went through all the rules. Let me remind you of one of the exercises we had. We said let's solve the following equation. 2 to the power of x is equal to 8. We did this by trial and error, by going through memory and figuring out that if you multiply 2 by itself 3 times, so if I have multiplying 2 by itself 3 times, well, that is what we write as 2 cubed, and that's what 8 is. Well, in this case, we were aided by round numbers and small numbers, so we could guess that the answer is 3. Sometimes it's not so straightforward as to what the answer is. Either it's not a whole number, or perhaps your numbers are big. We want to make a notation that is our aim. That is, we want to find this x in this context, given what? Given this base b and given this number on the other side. So the way we write the answer to this question is x is equal to, we use the word logarithm of 8 in base 2. So we take these two to mean the same thing. The first one is the one we are comfortable with, we are familiar with, 2 to the power of x is equal to 8. The second is whatever we do to extract that x, we call that set of activity. If you're using a memory, if you're using a table, you're using a calculator, we indicate that as logarithm of 8 in base 2. And while logarithm of 8 in base 2 is just this number. So let's go ahead and practice this in the context of several examples to make sure we are comfortable with what we are saying here. If I say 5 squared is equal to 25, what's another way of writing this? Another way of writing this is, for a second, let's imagine we didn't know what that exponent was, and if you want to extract it, whatever you do to get that extraction, you're doing it on 25 and 5. That extraction effort is written as logarithm of 25 in base 5. Let's do another one. Suppose I say 4 to what exponent is going to be 64. So numbers are getting a little bit bigger. So 4 times 4 times 4 is 64, and therefore x turns out to be 3. We got this thing by trial and error. And how we write it, we say logarithm of 64 in base 4, and that's what 3 is. Let's do another one. Suppose I write 10 to the power of y is equal to 1000. What is y? Well, 10 times 10 times 10 will be 1000. At the activity of extracting that the answer is 3, we write it logarithm of 1000 in base 10 is equal to 3. So 10 cubed is going to give us 1000 back. Let's experiment with some things less familiar. Suppose I write 5 to what power is 0.04. Okay, it's not likely that we immediately say what it is, but let's go ahead and experiment. This is 400th. Is that right? Which simplifies to 1 over 25. Which simplifies to 1 over 5 squared, which simplifies to 5 to the power of minus 2. So x which is logarithm of 0.04 in base 5, it actually turns out to be -2. Notice we went through a little bit of a contortion here to get the answer, but still it was available from our memory. 400th, we wrote it as a fraction, 4 over 100. We simplified to 125. We realize this is 5 squared. We realize the fraction is 5 to the power of -2. Therefore, we say x has to be -2. Let's do another one. Suppose I say 10 to the power of what number is going to be 0.001. So you want to pause this video for a second and try to answer for yourself. What is this decimal number? That is 1 over 1000. What's 1000? It's 10 cubed. What's 1 over 10 cubed? It's 10 to the power of -3. So here x, I can write it as a logarithm of 1000 in base 10, or I can write it as a logarithm of, write my fraction just as a fraction in base 10, that is -3. So if I have y is equal to b to the power of x, and now our focus is on x, we say x is same as logarithm of y in base b. These are saying the same thing for us. In this case, b is a positive number, and also it's different from 1, so to avoid some problems. These two, this is called exponential format. And this is called the logarithmic format. So we should be comfortable about going back and forth between these two cases. Since exponential is very important in finance, anytime that there's an interest rate, you are dealing with this function, you can imagine that logarithm will be closely related to that and close by. We said among all the bases there was one that stood out. In practice, base 2 or 10 are kind of common, but for mathematical reason and also from the origin in finance, there was a special number that we talked about. We said there is a special number E 2.71828, etc., as significant as the number pi. And if our base is this number, we have special situation. So y is equal to exponential of x. We write e to the power of x. E is not a variable, e is just this number. It's the definite number, but given that it's decimal, we just abbreviate it to e. It's the first letter of the name of a Swiss mathematician by the name of Euler. Okay, here we would have written x is equal to logarithm of y in base e. This function is so commonly used that has another name, another notation, is written as ln of y. L for logarithm and n for natural. So somehow this is the natural logarithm among all the possible choices. This one stands out. And e is sometimes referred to as the base of natural logarithm. So meaning the base that is used here. So the number E shows up in finance. If you invest $1 in an account that pays 100% interest and you compound that continuously, at the end of the year, instead of your dollar raise increasing to $2 because of compounding, it goes into this number, 2.72 almost. So you get an additional 72 cents out of this business of compounding. So exponential of x shows up in finance under so-called continuous compounding. Okay, most businesses do daily compounding and such, but sometimes they do monthly compounding. We have a mathematical version of that. The ultimate is called continuous compounding. It's like having your money, giving birth to money at every moment. So that is one of the origins of E. Might look like a weird number to you, but actually it comes from your neck of the woods. It's a finance. Originally it comes from finance, and then became very famous and important in mathematics all by itself. Okay, what we want to do is imagine what we're going to do. We had these rules of exponents here, really. These are everything about the exponents. Well, since logarithms and exponents are kind of mirror images of each other, they're inverses of each other, every rule that you have here is going to correspond to some rule about the logarithm. Let's go ahead and investigate that and see what are the rules of logarithm. So we are going to talk about rules of logarithm. So let's remind ourselves one more time. When you have 2 cubed equal to 8, you rewrite the same thing as logarithm of 8 in base 2 is 3. So think about it like this. 2 to the power of 3 is 8. Now let me ask you some logarithm questions. Suppose I ask you what's the logarithm of 2 to the power of 5 in base 2? Well, this is 32. We are asking what's the logarithm of 32 in base 2, but I'm making it easier on you. I say that 32 itself is 2 to the power of 5. Now we are asking what is the logarithm of that in base 2. Remember what happened here. The answer is whatever that it takes to take this raised to that exponent to get that. So we are asking 2 raised to the power of what is 2 to the power of 5. So that sounds a little bit silly because our answer is buried in the question itself. 2 raised to what is 2 raised to 5? The answer is, of course, just 5. Obviously, 2 to the power of 5 is 2 to the power of 5. So we have this rather odd-looking expression, a logarithm of b to the power of x in base b is just x, because b raised to the power of x is b raised to the power of x. Let me put this thing in parentheses so we are not confused about that. Okay, so that is one rule. We can say up front we have such a thing. Now let me ask you another question. For suppose I ask what's the logarithm of 2 cubed 2 to the power of 4 in base 2. Suppose we want to figure this out. So well, here's a multiplication. Let me use the rule of exponents there. It becomes 2 to the power of 7 in base 2. And just like here, logarithm of 2 to the power of 7 in base 2, what is that? It's just 7. Well, we could have gone from beginning to the end without any problem. 3 plus 4 is that 7. Now, what is that 3? That is logarithm of 2 cubed in base 2. That's 3. And what's that for? That's a logarithm of 2 to the power of 4 in base 2. Is that right? So that is same as logarithm of 2 cubed times 2 to the power of 4 base 2. What happens is that what we see here is true in general, meaning there's nothing special about the particular numbers that I use. I use numbers that are familiar to us. But if we had any number here, let's call this all of this number A, and 2 to the power of 4, let's call that number B. What this rule says is a logarithm of a product of two numbers is the sum of the logarithm of those two numbers. We don't need to know anything specific about the particular numbers themselves. We have the following: logarithm of a product is equal to the logarithm of one entry of the product plus the logarithm of another entry of the product. Nothing special about base 2 either. It can be any base. So just to avoid collision with this B that I have here, maybe I use the letter C. Logarithm of a product is sum of the logarithms. Let's go ahead and practice. Suppose I say expand. So when we go this direction, we say we are expanding the logarithm. We have more terms, more logarithms. And when we go in this direction, we say we are collecting the terms and we are condensing it. So what is the logarithm of A, B, C in base? Let's write this one K, so that again my letters do not collide with each other. So what do you think the answer is? It will be just like this one. You can show the logarithm of A in whatever base you are using, logarithm of B with whatever base you are using, and logarithm of C in whatever base you are using. So regardless of how many terms you have, you can apply this. Why is this rule so important? In a sense, this was a computer of its own time. When this idea came out in 16th, 17th century, this simple formula acted as the computer of its own time. Why is that so? Let me just give a brief explanation. You remember from elementary school that multiplying numbers was a rather painful chore. If you ever multiply two 5-digit numbers, you know how much effort it takes to do that. But what's happening here? You notice that on one side we have multiplication, on the other side we have addition. So logarithm is a machinery that converts multiplication to addition. And if you remember, well, adding two numbers was never as painful as multiplying the two numbers. So when this idea came along, the people could actually do various type of arithmetic, multiplication, division, powers and such by using rules of logarithm to simplify their task. And if you have ever seen a slide rule, perhaps belonging to your grandpa or something, maybe in an attic somewhere, that slide rule, which was again another calculator of its own time, was actually based on rules of logarithm. Well, you may be wondering what's the rule for division. If the logarithm is so great with multiplication, what does it do with division? And a good question. Logarithm of a fraction a over b in some base c is the logarithm of the numerator minus logarithm of denominator in the same whatever base you are having. They are all the same. Let's explain it like this. Suppose we want to figure out what is logarithm of 5 to power of 7 divided by 5 to power of 3 in base, let's make it simple, in base 5. Well, what would you have done here? You say, well, I can apply the rules of exponent to simplify that. So that's going to be 5 to power of 7 minus 3, that is 4. And logarithm of 5 to power of 4 in base 5 is just 4. Well, what is 4? You could have, from beginning, you could have subtracted these two, 7 minus 3. And who is 7? 7 is the logarithm of numerator, and 3 is the logarithm of denominator. Okay, now let me hide everything under, let's call this thing A. So this is my A, and let's call this one a B, and this is my B. Logarithm of A over B is a logarithm of A minus logarithm of B. The other details of the problem are not important at all. It could have been any number there. It would have been playing the same role for us. Okay, so this is another rule that we have. What other rule do we have that resemble the rules from exponents? Let me say logarithm of 1 in any base. Well, I'm trying to find a number such that when this is raised to that exponent, I get 1. We know the answer is 0 because we know c to power of 1, c to power of 0, c to power of 0 is 1. These are saying the same thing. What else? Logarithm of a fraction. Suppose I have 1 over a in some base c. Well, this is going to be logarithm of numerator minus logarithm of denominator by the rule that we had here. Well, logarithm of 1 we just learned is 0. So we are left with just logarithm of a in base c, but negative. So logarithm of 1 over a is minus logarithm of a in base c. What other rule do we have? We have another rule. Logarithm of a to some power n in base c is same as n times logarithm of a in base c. Let me explain this in a simple context. Suppose I ask you what is the logarithm of a squared in base c. I'll say a squared is a times a. And we just learned that if you are multiplying two numbers, taking logarithm, you can take a logarithm of individual numbers and add them up. All that has happened here is that our numbers have become identical, but same rule still applies. Logarithm of the first a in base c plus logarithm of the second a in base c. Well, if I add two things, what do I get? I get 2 of one of them, 2 of logarithm of a in base c. So all that has happened is that this became coefficient here. It is true for power 3, 4, and so on. It's true for any exponent in general is still true. So we have learned multiplication, division, and exponentiation. We have rules for all of them. There's only one rule left, and that is change of base. We have not been paying much attention to what base we have, but we have learned that there are several bases available. The natural base is that base e, which we talked about. We had the base e, We have base e, but in general people use either base 2 or base 10 because they are comfortable. 2 is used commonly with the computers. 10 with our everyday calculation, we always do things in base 10. So we want to be able to go back and forth between one base and another. So logarithm base e is important. It's a natural log. Logarithm base 10 is important because, well, the number 10 is so prominent in our life. So we have logarithm in base e and we have logarithm in base 10. Many books give these special short names. So for example, sometimes this is referred to as ln, short for natural logarithm. Some books have special notations for logarithm base 10 as well. And we said, since some people are very much interested in numbers in base 2 because of computers, that's another one. Well, you can have logarithms any base, just not to discriminate any number. If you wish, you can try to popularize logarithm base 7. You might not find that many takers and buyers, but that's a possibility. Logarithm in any base, so long as it's a positive number larger than, different from 1, it's a fair game. The question is, how do people compare these things with each other? How do compare one logarithm with another? And there is a simple formula that connects all of these things. Logarithm of x in base b. If you want to convert this thing to some other base, let's call that base c, say, for common. So logarithm of x in base c, if you take this and divide it by logarithm of b in base c, you get logarithm of x in base b. It kind of looks like dealing with fractions, but well, it's not. These are not fractions. Just looks like that. If you had simplified x over c with b over c, you would have gotten x over b, but that is just a coincidence. So this is the rule for change of base. So this is a change of base formula. Okay, so for example, suppose I want to find out what's the logarithm of 7 in base 11. Your calculator is not going to have base 11. It's not going to have some random bases. Most calculators just have base e or base 10. After all, there's a shortage of space on a calculator. You cannot put a button for every little something that you might come across. But what if you have to calculate logarithm of 7 in base 11? Well, you decide, for example, on what common base you want to use. Let's use base 10. You take the logarithm of both of these numbers in base 10 and divide them, and you get your logarithm. If you are partial to natural log, you can do that too. The formula looks cleaner because we don't write as much, but the idea is the same. Of course, if you had other logarithm accessible to you, you could have done that as well. We are going to have one more rule of logarithm, and that is, let me help you discover that yourself. So what is 5 to the power of logarithm of 125 in base 5? Let's go step by step. This looks complicated, but actually it's very easy. Well, first of all, what's a logarithm of 125 in base 5? We have practiced this thing. That is just 3. And now we are taking 5 and raise it to the power of 3 again. So what do we get? Obviously, we get 125 back. So I didn't need to waste time calculating this. This answer is whatever is in front of us over there. So if I have any number x to the power of logarithm of y in base x, even if these are not any friendly numbers, the answer that comes out is just the number y. Okay, now let's go ahead and paraphrase everything. What did we have? The logarithm of, let me use x and y and base b, x, y, in base b, logarithm of x over y in base b, the logarithm of x minus logarithm of y in base b, logarithm of x to the power of n in base b is n logarithm of x in base b. Maybe I can squeeze some of them. Logarithm of 1 over x is minus logarithm of x. Logarithm of 1 in any base b is 0. Let me write two of these rules at the same time. Logarithm of b to the power of x in base b is equal to x, and b raised to logarithm of x in base b is x. And let me put one rule here. Logarithm of x in base b is logarithm of, logarithm of x in base c divided by logarithm of b in base c. Let me see if I could squeeze everything in one page. Yes. And let's remind ourselves, when we say y is equal to b to the power of x, the definition of logarithm is that this is same as saying logarithm of y in base b is x. So if this is the first time seeing this thing, it might look mighty complex because everything sounds like everything else. But these are the rules of logarithm. Okay, so what we want to do is to practice some logarithmic problems for expanding or collecting. Remember, we said if you go in this way, you are expanding, and if you are going back, you are collecting into one term. We want to practice some of those, plus we want to practice equations involving logarithms, and also graphs of logarithms. Let's postpone that to the next lecture. Until then, good luck and God bless.